First, a little bit about myself. This is my GitHub handle. I am a maintainer of the open source etcd. What's this presentation for? I'm hoping that this talk will be helpful if you know Raft and you want to start reading, or you just started reading the Raft source code. I'm hoping that this presentation will give you a nice starting point on reading the code. And also, for those who wants to understand the relationship between etcd and Raft, basically how etcd uses Raft or why Raft is important to etcd, we're going to talk about this in this talk. And also, if you are writing your own project, your own application, you want to embed Raft package. Since we're going to talk about how etcd uses Raft, it can be an example of how your application uses Raft. All right, so this is today's agenda. First, we're going to do a very quick recap of the Raft so everybody is on the same page. And then the second point is we're gonna talk about how etcd uses Raft. And then we're gonna diverge a little bit from the second point. We're gonna talk about the third point, which is the implementation details of the Raft. And after the third point, we're gonna revisit the second point, because by then we're gonna have more details to talk about. And last, we're gonna talk about some of the ongoing effort I'm aware of in the Raft. Okay? All right, so Raft recap. First, quickly, some concepts. What is a quorum? A quorum is basically majority. So if Q1 and Q2 are quorum, their intersection is not empty. So what is a quorum? For example, if you have a cluster of size 1, so one server in your cluster, the quorum is 1. If you have 2 servers, your quorum is 2. But then if you have 3 servers, your quorum is not 3, it's 2, because you can pick any 2 out of the 3 and you can find intersection node between the quorum, right? So in this example, where you have five servers in your cluster, the quorum is 3. So here you can see these 3 becomes a quorum, and the next time these 3 becomes a quorum, and they do have an intersecting node, right? So what's the nice thing about Raft consensus protocol is that the entire cluster can make progress as long as there is agreement among the quorum. What does that mean? So in this example, you don't need all 5 servers to be available for you to serve the client. You can have at most 2 servers unavailable at the moment, but as long as you have quorum, which is 3, and if they agrees to something, the entire cluster can still serve client, right? So what is the problem Raft tries to solve? Imagine you have a collection of servers. Each server is a state machine. For example, in etcd is a key value store, right? You can write keys, you can read keys. It is a state machine. You have a cluster of servers. Each server is a state machine. Then when the client interact with this cluster, how do you make sure that from client's view, this cluster of servers behaves like a single state machine, a single reliable state machine? So for example, the client might, at this moment, right, it chooses to issue a write command. It writes a key value to the state machine, and one of the servers in your cluster served this request, let's say server A. And the next moment, the client wants to read that key, but server A is not available at that time. So it's a different server, let's say server B served the client. How do you make sure server B's local state machine has the same state so that when it serves the client, it returns the correct result, right? So that's the problem. How do you achieve a replicated state machine? Now, the nice thing about state machine is that a state machine, given its current state, given its current input, its next state and its output is determined. So if these state machines, if they all have the same initial state, which you have to make sure, right? So whatever bootstrapping process you're using, you have to make sure when these servers starts, they're gonna have the same initial state. And then if you can somehow achieve this, if you can make sure that each server also has the same input sequence, then it's guaranteed that basically so for these state machines, right, they're always going to have the same state and output, right? So the problem becomes, how do you achieve this? How Raft does it? So the Raft consensus protocol achieved this by basically doing this. It manages the replicate write-ahead log. So whatever the request the client wants to execute on the state machine, it first needs to be write to a log, which is managed by the consensus protocol. In our case, it's Raft, right? So it's the consensus protocol's job to make sure that these logs are actually coherent or the same across different servers in your cluster, so that because these are the input sequences to the state machine, right? So if these are the same, then when they input to a state machines with same initial state, then the problem is solved, right? Now, so how does Raft actually does it? Roughly speaking, it has two parts. First is leader election. The second is how leader replicate its logs to the rest of the servers in the cluster. So we're gonna first talk about leader election. A Raft node in a cluster can be either a candidate, a follower, or a leader. So term, what is the term? A term is basically a logic clock in the Raft. Starting of each term, there is going to be a election. So each node can vote for one node in a given term. When a node gets majority of the votes, remember the quorum we talk about? So if you get votes from a quorum, then it becomes a leader. So you can have at most one leader in a term. Now, once a leader is elected, it manages the rest of the term. The leader will periodically send out the heartbeat messages to make sure everybody else knows that the leader is still present, right? So this is the first step. Then, so now we have the leader, right? So the leader is responsible for manages those logs we just talked about earlier, right? So the leader is going to append to the log. So whenever there is a client request comes to the leader, that request becomes a new Raft log entry. The leader is going to append that entry to its own log. And then leader also keeps trying to replicate its own log to the other Raft node in the cluster. When majority of the node in the cluster has this particular log entry, so basically the logs are indexed. There is log entry 0, 1, 2, 3, 4, right? So the leader is trying to replicate these logs to the followers. The leader also monitors everybody's progress. Let's say node A has up to maybe log index 3. Node B has more logs, maybe has log 0 up to 6. So leader monitors the progress, and when it finds out the majority of the node in the cluster has a particular log, that log is marked as committed. So when it's marked as committed, it is safe for everybody to apply that log, right? In the example, let's say leader finds out, let's say leader has 10 logs, right, from 0 to 9, and remember, it tries to replicate logs to other nodes, right? Let's say there's 2 other nodes, node A and node B, besides from the leader, right? So node A has log 0, 1, 2, 3, and node B has 0, 1, 2, 3, 4, for example. Then, well, I guess since the leader and node B, they both have log entry 4, right? So from 0 to 4, they are all basically committed because you have majority of node have those logs. Once committed, it's safe to apply those logs. So each local node is gonna know from the leader which logs are committed, and it's gonna apply those logs, right? All right, so now let's talk about how Raft uses etcd. This graph is basically the same as the one we just saw. Remember, we already explained how a Raft can help to solve the replicated state machine problem, right? Now, in this graph, it's basically the same. Here is just a client. This is an example application. It's etcd Cuddle. It's a command line tool. It embeds the etcd client library. Another example can be in Kubernetes API server also embeds this client v3, which can talk to the etcd cluster. Now, when a client sends a request to the server, the request is routed to the Raft consensus module. For this example, let's say this server is a follower. It's not a leader, right? So let's say this is a cluster, and this is one of the server in the cluster, and it's not a leader, it's a follower. So once the request is routed to the Raft module, it's going to be forwarded to the Raft leader. The Raft leader will append that request to its own Raft log, and then it will try to replicate that log entry to other nodes. For example, this node showed here, right? This is a follower. And once it knows majority of the node has that particular Raft entry, it's going to be marked as committed. And now this server knows, okay, that particular log entry is committed, so I can apply that. So now it's going to be applied to this state machine, which in etcd is multi-version concurrency control key value store. So it's going to apply that to this machine. Remember, that log could be, it is a request from the client, right? For example, it can be read a key or write a key value. So whatever the output is, if you're writing, it's going to tell you, okay, write successful. If you're reading, it's going to return the value of that key, right? So whatever that applied result is, it's going to be returned, routed back to the client. Just quickly saying that because the server can crash and restart, it's very important that the input to the state machine and the state machine, they needs to be persisted on the disk, right? So when they crash and restart, they can replay whatever was before, so they can go back to the correct state. All right, so we're gonna revisit this graph later after we talk about Raft implementation. The design philosophy for the Raft package in etcd is that it tries to keep it minimalistic, meaning that the Raft package does not implement network transport between the Raft nodes. Remember, there are going to be messages between Raft nodes, right? Like just like we saw, the leader might replicate its logs to the follower. But this package does not implement network transport. Also, it does not implement the persistent storage layer. So whoever is using this Raft package needs to implement network transport and persistent storage layer. By including less in the Raft package, it makes the package more flexible because now you can choose your own implementation. It also makes the behavior of the Raft package to be deterministic. As a result, the Raft, well, deterministic is a very, very nice thing because if the behavior of the Raft package is deterministic, it usually means it's easier to implement, it's easier to test, it's also easier to argue its correctness. So the Raft itself is actually modeled as a state machine. Now let me go back to this graph. Now we're just going to focus on the Raft package implementation itself, right? So we're not talking about this state machine here. We're talking about Raft, and we're saying the Raft is modeled as a state machine, right? Just remember. All right, so Raft is a state machine, then what is its state? What is its input and output? How does state transition between each other? So now we're gonna dive a little bit into the code. Just a quick disclaimer, the code I'm showing here is mostly pseudocode so that they can actually fit in the screen and you can still see it. But they look very similar to the actual source code. So when you see this, and then later when you read the source code, it's going to be very familiar and it's easier for you to understand what the source code does, all right? So the state here is basically wrapped into this structure called Raft. You can see there is a node ID. There's a term, remember term is like a clock. Vote, each member can vote for one node in a term. So this indicates which node it voted. This is the log we talk about, like how, remember we said Raft consensus protocol helps manages the log to make sure the log on each node is the same. This is the log. And the state basically says a Raft can be either a leader, a candidate, or a follower. This is an interesting function. It's called step function. It has different implementations. Depends on if you are a leader, it's going to be a step leader function. If you're a follower, it's a step follower function, right, etc. Now, what's the input to the Raft state machine? It is a message. What is a message? First, it has a type. So messages are of different types. For example, you can have a message vote, which is for requesting a vote, or a message append, which is used by the leader when it tries to replicate its logs to other nodes. It's going to issue a message with a message append type. 2 is the destination node. From is where the message is from. We're going to skip this. And entries, so a message can carry a whole bunch of entries. For example, when the leader tries to replicate logs from itself to the followers, it's going to include the ref log entries here. Okay. What's the output of this Raft state machine? The output is wrapped into this structure, which is called ready. It means these are ready to be consumed, to be processed by whoever is using the Raft package. All right, so first one is the state of the Raft. Next one, this state needs to be saved to the storage because remember the Raft package itself does not include implementation of persistent storage, right? And these are the entries that needs to be saved to storage. These are the committed entries which are, remember, safe to be applied to the key value store. And these are the messages. Remember, the Raft package does not implement network transport. So it's whoever is using the Raft package needs to consume these messages and actually deliver these messages to their destinations. That's why they are included in the output. Now, how do the state transition? The core function is going to be the function called step with the capital S. Step function advance the Raft state machine using the given input. Remember, what's the input of the state machine? It's the message, right? So this is the input to the state machine, and you call this function. It's gonna advance your Raft state machine to the next state and output the thing here. If we look into this function, it eventually calls this function. And in the beginning, there's some common logic for no matter whether you're a leader, a candidate, or a follower. And then it calls this lowercase step function, which is different, depends on whether you're a leader, then this function is going to be called step leader, etc. Right? So it depends on your state, this function is going to be different. Now let's go to an example. How many times do we have? Okay. Now let's say we want to propose a change to the KV store, right? Remember, let's quickly go back to this slides. When a client requests to execute a command, for example, a read command or a write command to the key value store, it's gonna, so how it's gonna do, it's gonna propose a change to Raft. So this is the example we're going to talk about. So the first function is propose function. This data here is basically a serialized data. So for example, if you want to write something, it has a key and value. It's going to be the serialized, so that key and value serialized to the byte slice, right? So this data corresponds to the client's command. Now, what this function does is it generates a message and feed that message as an input to server's local Raft state machine. In this example, let's assume it's a follower who is serving the client request, okay? So what's in this message? You can see the type is message prop, and it includes the entries. This is the data. Remember, this corresponds to the client request, right? So this is the data. So this message, let's call it message A, goes into the follower Raft state machine. Now, if you go to the source code, remember it's going to be sent to the step function, which eventually, because it is a follower, it eventually goes to step follower function. Now this function depends on its input message. It's going to do different things, right? It's going to execute different code paths. In this example, because our input message is of this type, so it goes to this code path. And what it does is it basically mark a destination node to be the leader of the Raft cluster and send that message. What does send mean? Because remember, Raft package does not actually implement network transport between the Raft nodes, right? So if you look at this send function, this is basically marking this function, this message is from myself. Then it simply append this message A, right? This is the message M that is appended to its local message queue. And this message queue is going to be, so remember, the Raft state machine's output is something called a ready, right? It's a ready structure. Let's just quickly go back to make sure everybody still remembers. So this is the output of the Raft state machine, right? We just saw its input. Now its output is going to include this message A. See, this message A is appended to this message queue, then it's going to be included in this message. So what's the output of this follower Raft state machine? It's going to be a ready structure, but for simplicity, we're just tracking the messages, okay? The ready has other fields, but we're just tracking the messages. So it basically is the same message, right? But marked from itself and to the leader. We'll call this message B. Now, whoever is using this Raft package needs to process those messages, needs to process these messages from the output of the Raft state machine, right? In this case, these messages will be sent to their destinations. So let's look at the leader here. This is the same message B. It's going to be, so remember, you need to implement the network transport, right? So that network transport implementation needs to forward the message B from the follower's output to this leader's input. Now it's here. Let's look at step leader's function. Again, this is the message B here, and it's of this type, message prop. So let's see what leader does. It first appends all the entries from this message to its own Raft log. This is what it does. And then this function tries to append its Raft logs to other Raft nodes in this cluster. So let's say we have 2 other nodes in this cluster. It's gonna, for each of those nodes, it's gonna call this function, which is a new message of a different type now, message append, because now we're trying to replicate the leader's own log to other nodes, right? 2 is to that peer, then entries includes leader's own entry, commit we're going to talk about later. So this is basically, oh, actually we already talked about it, right? So when, because leader monitors each node's progress, when majority of those already have a certain entry, it's going to be marked as committed, right? So this is leader telling everybody the progress of the entire cluster, which means like which Raft logs are actually committed. And after it generates this message, it's going to send this message. This is the same send function we just saw. So this is going to be append to leader's local message queue, and eventually it goes to leader's ready output, the ready structure, right? Okay, so I think we are going to probably skip some of the steps. What I'm trying to show here is how to read the source code, like given an input based on whatever the current state is, whether you're a leader, whether you're a follower, it's going to have different state transition. And in return, it's going to generate more messages and maybe more entries. And they are going to show up in the Raft state machine's output, which is the structure we called ready, right? So maybe let's just fast forward to the last step of this example, which, so what we have seen, we've seen that, the client's request, which is the message A, included in this message A, was forwarded to the leader, right? We saw step 2. It's forwarded to the leader, appended to leader's local Raft log, and leader tries to replicate that Raft log to other nodes in this cluster. And eventually, it's going to be successful. So let's say most of the nodes already has this new Raft entry, and the leader knows that, and leader marks that new Raft entry as committed, and eventually it's going to send a message with the updated committed index. So when this message is received by the follower, the original follower, it knows, oh, that new Raft entry is committed, so it's safe to be applied. What happens then is that, because remember, this new Raft log entry is committed from the output of this follower's Raft state machine. From its output, you're going to see that new Raft entry show up here as committed entries. Now it's ready to be applied. All right, so this is the graph we just saw earlier. We're going to talk about with more details because now we're seeing more details. First, we don't care about the client side now. So the first thing we know is that the Raft package does not implement persistent storage interface. It does not implement network transport between the Raft nodes. So these are actually, if you are using the Raft package, you need to implement these. And then, if you're using this Raft package, you are probably going to end up with something like this, a handling loop. You're going to need to consume and process all the output from your local Raft state machine. So this gives you the ready structure we just saw. It's stored in here. The first thing you should do is this storage is your own implementation of the storage interface. You need to save the state, save the entries. And then the next step is that this is your own implementation of the network transport between the Raft nodes. You need to send those messages. Remember, you are responsible for actually delivering those messages. And then for all the committed entries, it's safe to be applied. So what's the life cycle of a client request? A client request is first going to be, remember, it's going to be routed to the Raft, and it's going to call this propose function, which generates a message, a Raft message, right? And within the Raft consensus protocol, it's going to, so the local Raft state machine is going to generate, based on that Raft message, it's going to generate a whole bunch of new Raft messages and be sent to other node. Another node in return might generate other messages, right? So it's back and forth, but eventually if that Raft log entry is committed, which means most node has that entry, eventually it's going to show up in your output field committed entries. So now the server needs to apply the committed log entries to the key value store, and the applied result is going to be sent back to the client. All right, so quickly, this is on some of the ongoing efforts I'm aware of. The first one is actually completed. So the Raft package itself supports learner and non-multi-member actually for a while now, but recently etcd server also adds support for learner and non-multi-member. If you're interested, here's the link for you to start. Another ongoing effort is that there's a Raft membership, there's joint consensus for Raft membership reconfiguration, which is different than the current membership reconfiguration implementation in Raft. If you're interested, this is the starting point for you. All right, so do we have time for Q&A? Oh, we have plenty of time. Okay, good. Any questions?
Hello 谢谢分享。就我想问一下，就是关于 Raft 的请求，就是它，比如说我的 get 一个 get 请求和一个 write 请求，然后它是不是有什么区别？比如说它是不是都会产生一条 Raft 的 log， 然后这个 log 是不是都会提交？然后它这个 log 是不是都会持久化到我这个本地的磁盘上？谢谢。
这个好很多。我怎么讲呢？就是基本上可以这么说，就是所有的这个 client 来的请求呢，因为我们可能因为为了确保正确性，所有的 client 的这个请求都要先写到这个 log 上面，就是在真正的去 execute， 在真正的去实施到你这个背后的 key value store 之前，都要写在这里。所以不管你是 read 还是 write 还是什么其他的 command， 但是其实这个就是说完了，就是你说的没错。但同时呢，如果你去读这个 Raft paper 的话呢，其实有一个特别特殊的情况，就是当你如果是一个 read request， 就是你要去读的话呢，其实你可以 bypass 这个 log， 你不一定要写在这个 log， 因为这可能我们下来谈吧。就是在 etcd 3.1 之后 ，linearizable 的 read， 就是正常的 read 的话是不需要再写在这里了。但是你也不可以直接 bypass 整个 Raft 去直接去读，这样也是不行的，因为你可能会读到错误的东西，因为你需要这个来确保正确性，对吧？所以它真正的情况是说，在你收到这个读的时候呢，你要问一下 leader 说，我们现在整个 cluster 认为我们应该 apply 到哪一个 entry 了。那么你在 local 的这个地方，你要等所有那些该 apply 的都 apply 完了，等于是你要把 latest 的之前所有的，在你接收到这个读请求的时候，你把之前所有大家已经同意的需要 apply 的那些 command 全部都 apply 完了以后，你才可以去读，所以是要稍微等一下，但是就可以 bypass 这个过程，不需要再做一个这个 disk IO 啊。
那也就是说 3.1 之前的话，它是要走这样一个流程。
对，你在 Raft log 里面是可以看到 read 的那个 entry 的。3.1以后应该是没有了。
好，谢谢。
好，还有问题吗？好，
你好，我问2个问题啊。
好。
第一个问题是说，如果我所有的那个 log 的更新都需要通过 master 的话，那会不会成为一个瓶颈呢？第二个问题是说，比方说我现在我的 client 跟我交互的是那个我的一个 follower， 然后那最后去改那个 key value store 的是我的 follower 还是我的那个 master？
是，那先一个一个回答。第一个问题，我觉得首先怎么讲？因为其实我们就先说 3.1 之前吧，就是你所有的 request 其实都要先记录在这个 log 上面，其实等于是你所有的 request 都已经 serialized 了，对吧？都已经 linearized， 所以本身瓶颈就已经在这里了。 然后到3.1以后呢，就是如果你是要读的话呢，其实你不一定要去 leader 那边读，你在 follower 这边也可以读，但是你需要先问一下 leader 现在状况是怎样的，然后你的本地可能需要等一下。刚刚第2个问题是什么？是这样子的，对，问题是说，如果是一个协请球的话，那个协请球如果跟它交互的 server 是一个 follower， 那么是 leader 还是 follower 在改那个 key value store 呢？那么 key value store 首先在每一个 server 上都有，然后你那个协请球呢，会首先那个 entry 会 forward 到那个 leader 那边，然后 leader 会 append 那个 entry 到他自己的 log 上面，然后那个 leader 之后呢，会把那个 log 它要 replicate 到其他的。包括 follower 上面，所以 eventually follower 也会有同样的 log。然后当大部分人都有了这个 log 以后呢 ，leader 会说好，现在就是很安全，大家把它 mark 成 committed， 现在可以去 apply 了。现在可以去 apply 的，那么就是只要有这个 log entry 的 node， 包括这个 follower， 它就会去 apply。apply 完了以后呢，这个 result 会返回给你这个给你交互的这个 client。
你好，我想问一个问题，就是其实是关于那个 log 去
理性一点。
就是我想问一个问题，就是关于那个 log 怎么去持久化的问题，就是因为那个就是我以前有朋友做相关的东西，他碰到一个问题，就是说他们在自己实现的时候，可能我一个比较直接的方式，我会去选择那个去同步的方式去最终调 fsync， 然后把 log 最终去写到盘上，但是这样也有一个问题，就是我可能 log 来的每次。假如说规模不大，我可能每次都要去调 fsync， 这样可能会有性能问题。就我想问一下，就是 etcd 这方面大概是怎么去做的？
这个我不一定说的是对的啊，因为这个其实是在 Raft 之外了，就是 etcd 里面它也是有一个 package， 如果大家去看的话，它就在那个根目录下面是叫名字可能稍微有点 confusing， 它那个名字叫 wal， 就是 WAL， 然后那个 folder 下面呢，其实 implement 的就是这个。就是这一部分，就是如何去交互的。我个人的印象中的话呢，它这个不是每个单独的 log entry 都会单独调一次 disk IO， 它应该是 batch 的。
它有没有就是去异步写盘的方式？就这块我也不是太了解，所以
你指的异步是哪个异步啊？
就是可能在我去真正做 fsync 的时候，我可以选择同步的，就是可能在一个 routine 里面同步的去存它，但可能也有一些其他方式。就是
我的理解是，这个讨论很好，这个你可以在那个 etcd 的那个 repo 上面去提交一个 issue 来问一下。我个人的理解是说，就是你怎么用这个 Raft package 的问题，就是你怎么去 consume 它的 output， 因为在 output 里面会给你这个 entries， 这个就是你需要去存到磁盘上面的 Raft log。那么这个具体怎么存的这个过程，我自己看到 etcd 使用 Raft 的话呢，它并不是异步的，它就是你需要先做第一步，先把 state 存了，把 Raft log 存了，然后再把 message send 给其他的 Raft node， 然后最后再去 apply 这个 committed entries。这个是我看到的，我觉得这个顺序肯定是对的，但是你想说异步来去做，有没有可能有其他问题？这个我可能回答不了，但是欢迎去提一个 issue， 然后大家可以讨论一下。
好的，谢谢。
你好，我想请教一下，就是那个 etcd 里应该记录的数据大概有2类，一类是 object， 还有一类是 event， 这种2种数据，对吧？
哦，你说的是那个 Kubernetes 里面用 etcd？
对。然后就是随着集群这个运行时间长，它那个 event 应该很多。那它会对这个 event 数据做清理，或者是就是释放空间？
这个可能我不是很熟悉啊，可能在座有熟悉。我的理解 events 是有 TTL 的，对吧？那个 TTL 是可以设的，就那个 events 会 attach 一个 list， 然后那个 list 我可能记得 default 是1小时还是多少的，就是它会被清掉。
就是 TTL 之后的话，它会自动
清掉
是吧？不会记录在OK。
你好。
好，你好。
你好。
可以，有点声音有点小，
就是问一个 etcd 功能方面的一个问题，就是我们遇到一个问题是我们现在是3套，比如说3套那个 etcd 的集群，然后我们想通过一个改造把3套的集群的数据合并到1套里面，有没有现成的这种工具或者方法？
哦，这个和这个我们可以私下聊吧，这个和这个关系不是特别大，好吧？私下讨论一下。我们时间是不是差不多了？好，那谢谢大家，非常感谢。